Okay, number 12 is a problem that people ask about every year, and I totally get why. What bothers people is this weird little cursive L right here. And, I like to think that here in AP Calculus, you guys are making the jump here from kind of, lower level math to higher level math. Well, a lot of higher level math is going to deal conceptually in kind of this abstract realm rather than in the concrete realm you guys are used to. But if you can train your brain to kind of just be quiet and realize that L really isn't any different than if we had a number there like 5 or 7, some of these problems get a little bit easier. So what's going on here, guys? Our base of our solid, the concrete foundation we're going to pour, is a square, one of whose sides is the interval from 0 to L along the x-axis. Now, the fact that they wrote the interval in this order, with 0 coming first and L coming second, tells you that L has to be greater than 0. So I'm going to just go a random amount over here to the right and say, okay, that value is L. Think of it as a 5 or a 7 if that makes you feel better. And so this little segment that I'm drawing here in blue is one side of our square base. Now, it actually doesn't tell you whether this square is going up here in the first quadrant or down here in the fourth. It actually doesn't matter though, guys. You're going to get the same volume either way. So I'm going to go ahead and let's try to make this easy. And I'm going to assume that this square goes into the first quadrant now. Okay, and that's what we've got. Now, pardon me for saying something probably dumb, but if it's a square, how long does each side have to be? From 0 to L is a length of L, and since it's a square, the height needs to be exactly the same as the width, so this is an L by L square. You can think of it as 5 by 5, 7 by 7, whatever you want to think of it as. So that base right there, guys, that's our concrete foundation. And then from that concrete foundation, what are we building? We are drawing cross sections here. Oh, here it is again. I wish they mixed this up a little bit more. Perpendicular to the x-axis. So yet again, this is a dx problem. So I'm going to draw a segment here perpendicular to the x-axis, looking like that. And eventually I'm going to draw rectangles whose heights are x squared, but I don't need to worry about that just yet. Now, this problem is different than the last couple ones that I did, because in this problem here, going back to number 11, let me get rid of my shading. If I were to move this line segment here from left to right, you'll notice, guys, the length of this line segment has to change. It would have to get, let's see, I drew it right here. It would have to get shorter as it moved to the right, longer as it moved to the left. So that is why S is a variable quantity, so S contains the variable X. The exact same thing happened over here in number 9 with that B that I drew right there that's really hard to see now. Again, B is a variable quantity, so its expression contains an X, a variable. But in this problem, you guys, if I take that segment there and I move it a little bit to the left or a little bit to the right, because our concrete foundation, our base is a square, that piece right there is going to remain constant. Now, I usually would call that B because that is the base of a rectangle, and I would ask you guys, okay, how long is B? Well, the weird thing about this one is it doesn't matter what your x coordinate is. The length of B is always going to be equal to the length of L. So B is simply equal to L. And there is no variable in that expression, guys, because yet again, B is a constant amount. It's not going to change as you move it from left to right. Now, if I wanted to draw my three-dimensional figure here, okay, it would probably look something like this and something like that. Okay, there you go. And then here's your red segment right there. That would be the base of your rectangle. And the height of that rectangle is not exactly easy to see. They're telling us that the height of that rectangle is simply going to be x squared. Whatever your x coordinate is, you're going to square that. So let me just guess here, guys, that if this x coordinate was 3, there I'd be saying that L would have to be greater than 3. But if that x coordinate is 3, that would mean that the height of this rectangle was 9. If this was a 4, well, you square that 4, your height is going to be a 16. And what that actually means here, this gets interesting, if you wanted to try to get this in there, is that the cross section of this thing, the shape, is going to kind of look like a parabola that opens up like this. And this is essentially the shape that you're building, kind of like a skateboard ramp, but probably steeper than you would want it to be. Anyway, that's what we're building right here. So the base of that rectangle is going to have a length of L. And so what do we know, guys? The area of a rectangle is simply going to be its base times its height. We would want all that expressed in terms of x. So area as a function of x is going to be, well, b, we said was always equal to L, which remember is not a variable, it's a fixed constant. And the height of those rectangles, given to you right here, the height is always going to be x squared. You can't simplify that expression at all, guys. So the area of every one of these rectangles here is L times x squared. Okay, that's as much as we can do with that. So our volume then will be a definite integral, we said a while ago, taken with respect to x, of this expression right here, L x squared. And since L is a constant, I'm going to bring it all the way out in front and just leave the x squared now as my integrand. All I'm missing are the limits of integration, lowest and highest values of x. So this region begins right here, guys, when x is 0, and it ends right here when x is L. So a little bit odd, but that L shows up twice here. So what do we have? The L out in front, and then in brackets, antiderivative of x squared, I think this is the third problem in a row where this has happened, is a 1/3 x cubed evaluated from 0 to L. So let's see what that gets us. L out in front, and then in the brackets, 1/3 times L cubed can't be simplified, so that's what it is, and then minus 1/3 times 0 cubed is just a 0. So that 0 does nothing for us, and the L times 1/3 L cubed is going to be a 1/3 L to the 4th power. Cubic units, because it's a volume problem, and that's as much as you can do here, guys, and that's our answer to number 12, 1/3 L to the 4th.